So I'm saying that this equation, this is a solution to a sixth order non-homogeneous linear constant coefficient differential equation. And the question is, what was the question? So let's find that differential equation. So I look at it and I see pieces that could be done. Remember, it's linear constant coefficient, so eigenvalues are going to be key. This piece here, the ln of t plus 1, that's not anything that I would get. That's not a piece that would come about by one of the eigenvalues. So that must be the particular solution. Remember that a solution should be the homogeneous solution plus the particular solution is equal to the general solution. And what we're seeing here is the general solution. So this piece must be the particular solution. So we would normally write it as homogeneous plus the particular. So I'm just going to put that over here. So now this must be the homogeneous solution with the constants in it. So our first question, we figured out that that's the particular solution, the ln of t plus 1. Now, to get the question, we need the differential equation, which should be sixth order, so what are the eigenvalues? We also need the initial conditions. So if it's a sixth order, I get 6 initial conditions. If it was first order, I would get 1 initial condition. I would have y naught equals a number. This is sixth order, so I need y prime naught equals a number, y prime prime naught equals a number, etc., all the way up to the fifth, derivative. So I need y naught equals, y prime naught equals, y prime prime naught equals, y prime, all of them. So to get y naught equals, remember I'm getting the initial conditions now, I'm skipping this eigenvalue thing, I'm just talking about the initial conditions. I can just plug t equals 0 into this, and that will give me y naught equals. If I plug t equal to 0, that's going to be e to the 0 is 1. This piece becomes 0 because of the t squared. Cos of 0 is 1. E to the 0 is 1. So this becomes 2 minus 0 plus 2. And if I put 0 in here, ln of 1 is 0. So y naught equals 0 is our first initial condition. So if I'm looking for initial conditions, then I've got y naught equals 0. And I need now the y prime naught, the y prime prime naught. I've got the answer, so I just need to differentiate this 5 times. Just to save time on the video, you don't want to watch me differentiate this. We can differentiate this. You can differentiate this. That'll be something to do at home, I guess. So here's y prime naught, I differentiated it. Y prime, I differentiated it. Now I'm going to sub in t equals 0. So there's the derivative. When I make t equals 0, e to the 0 is 1. There's a t there, so when I sub in 0, that piece disappears. 1 over 0 plus 1 is just 1. Cos of 0 is 1. E to the 0 is 1, so this piece is just 14. Sine of 0 is 0, so that disappears. With the t squared there, when I plug in 0, is 0. And so I get 2 plus 1 minus 14. I'm getting minus 11. So y prime naught equals minus 11. I need y prime prime naught, etc. So I've pre-done all this. There's the derivative. I'm just differentiating the y prime to get the y prime prime, subbing in 0, and I get minus 41. Differentiating it again, subbing in 0, gets 686. Differentiating again because I need the fourth derivative. So differentiating this again, plugging in 0, I get y, the fourth derivative, prime 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 prime, equal to 12,906. And one more, the fifth derivative, because it's a sixth order differential equation, I get 6 initial conditions, y naught, y prime naught, y prime prime naught, etc., all the way up to the fifth. We'd normally write this with Roman numerals. I didn't. Taking the derivative, plugging in 0, I get this 118,332. All right, so getting the initial conditions. Remember, I want the question. I picked out, here's our answer. I picked out what the particular solution could be. The rest of the stuff I'm leaving as the eigenvalues, and I've already got the initial condition. Let's get the eigenvalues so we can get the question. If it's sixth order, I need 6 eigenvalues. So this piece looks like, if I had lambda equal to 1, this would be some constant e to the 1t. So that looks like one of the eigenvalues. This next piece has a t squared on it. So to me that's saying repeated eigenvalues. 3 is an eigenvalue, but it must be repeated 3 times because there's probably I'm inferring that there's a 0, remember all the constants are there, 0 times e to the 3t for the first eigenvalue, and there's a 0t e to the 3t, and now there's a t squared. So this is what I would write if I had eigenvalue 3 repeated 3 times. Put it down once like normal, second time throw a t in, third time throw a t squared in the front, but these coefficients must have been 0, that's why I don't see them. Now I've got 4 of the eigenvalues. Well, the trig is going to be trig's going to give me 2 eigenvalues. Real part, e to the real part, t, trig imaginary part, so that must be 7 plus or minus 6i. So now I've got 1, 2, 3, 4, 5, 6. I've got the 6 eigenvalues that I need. Where's the cosine part here? There's the cosine part. Where's the sine part? The sine part, again, it must be, they come in pairs. The sine part must have had a coefficient of 0, and that's why I don't see it. So now I've got my 1, 2, 3, 4, 5, 6 eigenvalue pieces and my particular solution. So 6 eigenvalues. The eigenvalues are the roots of the characteristic equation. So the characteristic equation must have been lambda minus 1 for the eigenvalue of 1, and lambda minus 3 cubed for that repeated eigenvalue of 3, 3, 3. When I list the eigenvalues, I don't want to just write 3. I want to make sure that people know that it's a repeated eigenvalue, so that's why I would write 3, 3, 3. And now the trig piece. The trig piece is going to be tricky. Let's do this one separately. So I still want lambda minus, that'll be 7, I'll use the plus 1, so minus a minus is a plus, times, this one would be minus 7 plus 6i. So I'm still putting them in as roots, but I want to just expand that out. I'm going to multiply that out. Whenever I get a 6i and a 6i, that's going to be 36i squared, so minus 36. Let's just expand this piece out. Okay, so I multiplied it. There's no i's? Yeah, because there's no i's because the I pieces cancel out. So there's the auxiliary equation that would produce these 6 eigenvalues. I'm going to expand out this auxiliary equation. I've expanded out this auxiliary equation, and now I can write the 6th order differential equation. This lambda to the 6 must be y prime 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 prime, the 6th derivative. Let's write it like this so we're not counting. So that's going to be Roman numerals, the 6th derivative, minus 24, the 5th derivative for the lambda to the 5, plus 261 y, let's keep with the Roman numerals, minus 1408. 1408, that'll be, now I can, y prime prime prime, plus 3843 y prime prime for the lambda squared, minus 4968, 1 lambda, 1 prime, and finally that 2295 should just have a y in it. This will be the homogeneous equation then. This homogeneous equation would produce this auxiliary equation. When I factor, I would get this factored auxiliary equation. characteristic equation, sometimes people call it, and that would give me the eigenvalues that I see, the 1, the 3, 3, 3, and those two complex conjugate pair of 7 plus or minus 6i. All right, but this is not the differential equation yet. That's just the homogeneous part. It's not the differential equation because it's not homogeneous. So there's equal a g of t there. How do I find the g of t? That's where the particular solution goes. When I put this particular solution in the left side of the differential equation, the g of t will pop out. All right, now I need to have, I've got the y that's going to go in here. It's the ln of t plus 1. I need its derivative, I need its second derivative, I need its third derivative, I need its fourth, fifth, sixth derivative. I got to differentiate this 5 times and then plug it in the equation and see what the g of t is equal to. That's what the particular solution is supposed to be. So I need y particular prime. Okay, so there's me differentiating the particular solution. Now I need y prime prime particular. I have to differentiate this again. And I have to differentiate it again. The minus 2 comes down. That makes that a plus 2. Subtract 1 from the exponent. And so on and so on. Let me just skip ahead and I'll throw down all the other derivatives. So now I've got the particular solution. It's first derivative, second derivative, third derivative, fourth derivative, fifth derivative. I just need to take these pieces and plug them into their spots in the differential equation to figure out what g of t is equal to. Okay, there's the sixth derivative. That piece goes in here. I need the, okay, I already put in that's the sixth derivative, fifth derivative. I need the fourth derivative, third derivative, second derivative, first derivative, and the actual function. Oh, and if I would clean this all up, it won't clean up nice, but if I did, that would equal to the g of t. I don't even have to clean it up. That is the g of t. So we had our differential equation here, except for I didn't have the g of t. Now I have the g of t. So let's actually throw down the answer then. The final answer is going to be this piece, this, and equal to this g of t. And I'm not even going to simplify it, because I don't want to. Can I simplify this piece? It simplifies a bit. Okay, without the ln. So let's put that in for this to see if it cleans up a little bit. Okay, I got to make the face small so I can see it. Here's the differential equation, the sixth order differential equation. The auxiliary equation will give me the eigenvalues that I see. This particular solution is what I would get if I put in, or this g of t, this target solution, is what I would get if I put in this particular solution into the left-hand side of the differential equation. So, go back to what's the question? What are we actually doing here? Here was the answer, and we're asking for what's the question. This must be the differential equation for which this is the general solution, with the particular solution of ln of t plus 1, and the rest of the pieces being the homogeneous solution. So this is our differential equation. It's sixth order, so we also get 6 initial conditions. We have y naught equals 0, y prime naught equals minus 11, etc. So we've got all the initial conditions. So I suppose we've answered this question backwards. What was the point of all this? The point of this is the eigenvalues are your connection between the answer to the question and the actual question. You can go from answer to question, or the more normal way to do it is from the question to the answer. But we can start the process at any point and get the whole thing. From the question to the answer, we can create the whole thing from just one of the pieces as a clue.